There was nothing, not darkness, because darkness is something. Not silence, because silence requires space to be silent in. Not emptiness, because even emptiness is a container waiting to be filled. There was no waiting, no container, no concept of before or after, here or there, possible or impossible. Imagine trying to picture a color that doesn't exist, a sound beyond the range of anything that could ever hear it, a moment outside of time itself. You can't. Your mind recoils. It searches for edges, for reference points, for some foothold in the familiar. But there were no edges. There was no stage upon which events could unfold, no canvas upon which reality could be painted, no clock ticking toward something we might call a beginning. This wasn't a void waiting to be broken. It was the absence of absence itself, a concept so complete in its nothingness that even calling it nothing gives it too much credit. And yet, here you are. Here we are, reading these words, breathing this air, orbiting this star in a universe so vast that light itself takes billions of years to cross it. Everything around you, every atom in your body, every photon striking your retina, every thought firing through your neurons, emerged from that impossible nowhere, somehow, in defiance of every intuition you possess. Something came from nothing. The universe wasn't created in that nothing. The universe, along with time, space, matter, energy, and the very laws that govern them, exploded into existence together. All at once. In a singular eruption we've come to call the Big Bang. But that name is a lie. There was no bang. Sound requires air, requires atoms vibrating, requires a universe that already exists. There was no explosion in space. Space itself was the explosion. How does something come from nothing? The question haunts us because it shouldn't be possible. Every rule we know, every law carved into the bedrock of physics, tells us that matter and energy cannot be created or destroyed, only transformed. Cause must precede effect. For every action, there must be an equal and opposite reaction. The universe seems to run on a cosmic ledger where the books always balance, where nothing appears without something else paying the price. And yet, 13.8 billion years ago, that ledger was thrown out entirely. The universe didn't emerge from something else. It didn't transform from a previous state. It simply began in a flash of creation so absolute that the word began itself becomes meaningless. Because before that moment, there was no time for anything to begin in. This paradox kept philosophers awake for millennia. If everything needs a cause, what caused the first cause? If God created the universe, what created God? If the Big Bang started everything, what started the Big Bang? The questions spiral inward like an infinite regression, each answer spawning a deeper question, until we're left staring into an abyss that stares back with equal confusion. Ancient thinkers invented creation myths to paper over this void. Cosmic eggs hatching into reality, God speaking worlds into being, eternal cycles of creation and destruction where the universe breathes in and out like a sleeping giant. But these were stories, beautiful and comforting, designed to give pattern to the patternless, meaning to the inexplicable. Then came the detectives, not priests or poets, but scientists armed with mathematics and telescopes, ready to interrogate the universe itself for answers. In 1929, Edwin Hubble pointed his telescope at distant galaxies and noticed something impossible. They were all rushing away from us, not just drifting, fleeing, as if repelled by some invisible force. The farther away a galaxy was, the faster it receded, hurtling through space at speeds that seemed to violate common sense. But Hubble realized what he was seeing wasn't galaxies moving through space. It was space itself expanding, stretching like a balloon being inflated, carrying galaxies along for the ride. If the universe was getting bigger, that meant yesterday it was smaller. Last year, smaller still. 1 billion years ago, incomprehensibly denser. And if you ran the clock backward far enough, rewinding the cosmic film to its opening frame, everything, every galaxy, every star, every atom collapsed into a single point of infinite density and temperature. A singularity. The universe had a birthday. Georges Lemaitre, a Belgian priest and physicist, called it the Primeval Atom, a poetic name for an idea that shattered everything humanity thought it knew about existence. The universe wasn't eternal. It had a beginning. Time itself had a starting line. But this raised more questions than it answered. What was the primeval atom made of? Where did it come from? And most disturbing of all, what happened before it? Stephen Hawking spent decades wrestling with that final question, and his answer was both elegant and maddening. There was no before. Asking what came before the Big Bang, he explained, was like asking what's north of the North Pole. The question is grammatically correct but conceptually meaningless. Time is a dimension, like space, woven into the fabric of the universe itself. Before the Big Bang, there was no fabric, no dimension, no stage for events to play out on. The universe didn't begin in time. It began with time, space, matter, and energy all erupting simultaneously in a creation event so total that nothing outside it can be said to exist. But here's where the story turns strange. What we're about to discover will rewrite everything you thought you knew about beginnings. Because some scientists now believe the Big Bang might not be the beginning at all. It might be a transition, a bounce, a moment when a previous universe collapsed into ours. Or it might be one bubble in an infinite foam of universes, each with its own Big Bang, its own laws of physics, its own story of creation. The void before everything might not have been empty at all. It might have been pregnant with infinite potential, a quantum field seething with possibilities, waiting for the right fluctuation to tip it over the edge into existence. The universe might be older than time itself, stranger than we can imagine, and more mysterious than we ever dared to fear. What felt like a beginning might just be the only chapter we're capable of reading. The universe exploded into existence at precisely 0 seconds, but to call it an explosion is to miss the violence entirely. There was no fireball expanding into empty space, no shock wave rippling outward from a central point. Instead, space-time itself detonated, and in the first trillionth of a trillionth of a trillionth of a second, a span so brief that no clock could measure it. No human mind could fathom it. Everything that would ever exist was forged in conditions so extreme they make the core of our sun look like a frozen wasteland. This moment, this infinitesimally thin sliver of time called Planck time, measured at 10 to the negative 43 seconds, represents the absolute edge of what physics can describe. Before this instant, our equations collapse into gibberish. The laws of nature themselves hadn't yet crystallized. Gravity, electromagnetism, the forces that hold atoms together and tear them apart. None of it existed in recognizable form. There was only a roiling quantum foam, a seething probabilistic chaos where particles flickered in and out of existence like static on a television screen tuned to a dead channel, where space and time themselves were uncertain, granular, pixelated at scales so small that atoms seem as vast as galaxies by comparison. And then, in that first incomprehensible flash, something extraordinary happened. The universe chose to exist. Not gradually, not tentatively, but with absolute commitment. Space-time unfurled like a flag snapping in a hurricane wind, and reality crystallized from the quantum foam with a suddenness that beggars description. Temperature soared to 10 to the 32 degrees Kelvin, a number so large it's essentially meaningless, except to say that if you could somehow compress all the heat of every star that will ever exist into a volume smaller than a proton, you'd still fall short by factors of billions. At these temperatures, matter as we know it couldn't exist. Atoms? Impossible. Molecules? A joke. Even protons and neutrons, the building blocks of atomic nuclei, were too complex, too cool to survive. Instead, the universe was a soup of fundamental particles and energy so dense, so hot, that the line between them blurred into irrelevance. But here's where the story becomes almost unbelievable. In less time than it takes light to cross the diameter of a proton, in fact, in far less time than that, the universe underwent a transformation so radical, so explosive, that the Big Bang itself seems like a gentle whisper by comparison. This was inflation, a period of exponential expansion driven by a mysterious energy field that physicists still don't fully understand. Imagine a snowflake crystallizing in reverse, but the snowflake is the universe, and instead of forming intricate patterns, it's tearing apart at speeds that violate everything we think we know about motion. In 10 to the negative 35 seconds, that's a decimal point followed by 34 zeros and a 1, the universe doubled in size, then doubled again, and again, and again. 100 doublings in a span of time so brief that calling it an instant gives it too much credit. Let's put that in perspective. You blink, and roughly a tenth of a second passes. A hummingbird beats its wings, and 1/100th of a second ticks by. Light, the fastest thing in the universe, crosses the width of a single atom in about 10 to the negative 19 seconds. That's already impossibly fast. But inflation happened in 10 to the negative 35 seconds. And in that span, the universe expanded by a factor of at least 10 to the 26. Something smaller than a subatomic particle ballooned to the size of a galaxy. Some models suggest it grew even larger, perhaps to the size of our entire observable universe or beyond. All in less time than light could cross a distance smaller than anything that exists. And here's the paradox that breaks our brains. The universe expanded faster than light. Not faster than light traveling through it. Faster than light could possibly go, even in a perfect vacuum. Einstein's relativity tells us nothing can exceed light speed, that it's the ultimate cosmic speed limit, written into the structure of space-time itself. But inflation didn't move things through space-time. It expanded space-time itself, stretching the fabric of reality like taffy pulled by invisible hands. The galaxies weren't racing apart. The space between them was multiplying, and space-time doesn't have to obey speed limits because it is the thing those limits are written into. It's like painting dots on a balloon and then inflating it. The dots don't move across the rubber surface. The surface itself expands, carrying the dots along for the ride. Except the balloon is the universe, and it's inflating trillions upon trillions of times faster than seems remotely possible. But where did the energy for this come from? Here we stumble into one of the deepest mysteries in physics. Energy can't be created or destroyed. That's the first law of thermodynamics, carved into granite as one of the unbreakable rules of reality. Yet inflation required enormous amounts of energy to drive that exponential expansion. The answer lies in a quantum loophole so elegant it feels like cheating. The inflation field, sometimes called the Inflaton, was a temporary energy field that permeated all of space-time in those first moments. Think of it as a false vacuum, a state where the universe was balanced on a knife's edge, pregnant with potential energy just waiting to be released. When the inflaton field finally decayed, all that potential energy converted into real particles, real matter, real radiation. The universe didn't violate conservation of energy. It borrowed against the future and then paid itself back in the currency of existence. This is where the fundamental forces began to split apart. In the unimaginable heat of Planck time, all four forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. The universe operated under one law, one elegant mathematical symmetry that governed everything. But as inflation cooled the universe by stretching it thin, that symmetry shattered like a crystal struck with a hammer. First, gravity split off, becoming its own distinct force, weaker than the others but infinite in range. Then, as temperatures continued to plummet, and by plummet, we mean dropping from incomprehensibly hot to merely trillions of degrees, the strong nuclear force separated, followed by the electromagnetic and weak forces diverging from each other. Each split was a phase transition, like water freezing into ice, where the rules of reality rearranged themselves into new configurations. The universe was writing its own instruction manual as it expanded, deciding on the fly what forces would exist, how strong they'd be, how they'd interact with the matter that was about to appear. And matter did appear, but not in any form we'd recognize. The first particles to condense out of the energy were quarks and gluons, the fundamental constituents of protons and neutrons. But they didn't exist as discrete particles yet. They formed a Quark-Gluon Plasma, a state of matter so hot and dense that individual particles couldn't form stable identities. They swapped and merged and separated in a roiling chaos, bound together by gluons, the carrier particles of the strong force, which are so peculiar that they carry the very charge they're supposed to mediate. It's like a messenger who not only delivers letters, but becomes part of the message itself, tangling and binding in ways that make the strong force the most powerful in nature. Floating through this plasma were leptons, electrons, and their heavier cousins, muons and tau particles, along with neutrinos. Ghostly particles so reluctant to interact with matter that trillions pass through your body every second without you ever noticing. And threading through everything was light. Not light as we know it. Not photons streaming through empty space, but a thick, opaque radiation that couldn't travel more than a tiny fraction of a distance before being absorbed and re-emitted. The universe at this stage was a fog, a blinding, seething fog where light was trapped, bouncing endlessly between particles in a cosmic game of pinball that wouldn't end for another 380,000 years. But the real magic was happening on scales we still can't directly observe. Quantum fluctuations, tiny, random variations in the density of the Inflaton field, were being stretched by inflation from subatomic scales to cosmic scales. Imagine taking a photograph and zooming in on a single pixel, then blowing that pixel up to the size of a billboard. Inflation did this to quantum uncertainty, taking microscopic wrinkles in the fabric of space-time and amplifying them to galactic proportions. These fluctuations were tiny, differences in density of perhaps 1 part in 100,000, but they were enough. They would become the seeds of everything, every galaxy, every star, every planet, every atom in your body traces its ancestry back to a quantum fluctuation that occurred in the first trillionth of a second after the Big Bang. Randomness, stretched to cosmic proportions, became the blueprint for structure itself. Then there was the Higgs field, perhaps the strangest player in this cosmic drama. The Higgs field permeates all of space-time, even now, even here, even in the emptiest regions of intergalactic space. It's a field that gives particles mass through their interaction with it. Particles that interact strongly with the Higgs field, like quarks and electrons, acquire significant mass. Particles that don't interact with it at all, like photons, remain massless and travel at the speed of light. Before the Higgs field settled into its current state, particles were massless, zipping around at light speed, unable to clump together, unable to form the structures that would eventually become atoms and molecules and us. The Higgs field underwent its own phase transition, like water freezing, and when it did, it broke yet another symmetry, giving the universe its current character. This field is so important that scientists spent decades searching for evidence of it, finally detecting the Higgs boson, the particle associated with ripples in the Higgs field, at the Large Hadron Collider in 2012. Finding it confirmed what theorists had suspected. The universe had to acquire mass in order to become interesting. The elegance of all this is staggering. From chaos came order, not despite the violence, but because of it. The laws of physics didn't exist before the universe. They emerged from it, crystallizing out of symmetry breaking as temperatures fell and the Inflaton field decayed. It's like watching a piece of music freeze into ice, where every note, every harmony, every rhythm is locked into crystalline structures that we can study and measure. The violence of creation. Particles annihilating in floods of energy. Space-time tearing apart faster than causality could keep up. Temperatures that would vaporize matter before it could even form gave birth to mathematical elegance so precise that we can predict the behavior of particles to 15 decimal places. Yet for all this precision, inflation left something behind, a scar, a signature. When space-time was stretched by inflation, those quantum fluctuations we mentioned earlier were frozen into the fabric of the universe itself. They created tiny variations in the density of matter and energy, variations that would eventually drive the formation of galaxies. But they also created something else. Gravitational waves, ripples in space-time itself, like the wake behind a boat on a still pond. These primordial gravitational waves are almost impossibly faint, but they're still there, still propagating through the universe after 13.8 billion years. carrying information about the instant of inflation itself. We've detected their echo. In 2013, a satellite called Planck mapped the cosmic microwave background, the afterglow of the Big Bang, in exquisite detail, finding patterns that match the predictions of inflation to astonishing accuracy. Those tiny hot and cold spots in the microwave background are literally the imprint of quantum fluctuations from the first moments of time, now stretched across the entire visible universe. We're seeing baby pictures of reality itself, snapshots taken when the universe was less than a second old, encoded in radiation that has been traveling for billions of years to reach our telescopes. But this cosmic scar is hiding a secret. The patterns in the cosmic microwave background tell us about inflation, yes, but they also hint at something deeper. Some physicists believe these patterns encode information about what came before inflation, before the Big Bang, before time itself in the conventional sense. The universe might have existed in a different state, a previous universe that collapsed into ours, or a quantum vacuum that spontaneously fluctuated into existence, or something even stranger that our mathematics can barely describe. The scar inflation left behind isn't just evidence of a beginning. It might be evidence that the beginning wasn't the beginning at all. And that realization opens a door we're only now learning how to walk through, into a territory where creation and destruction blur together, where universes might be born and die in an eternal cosmic cycle, where the question, what came before, might finally have an answer, just not one we ever expected. Light was born in the first instant, but for 380,000 years, it was a prisoner. Imagine a universe flooded with photons, brilliant beyond description, but so choked with matter that no particle of light could travel more than a whisper before being swallowed and re-emitted, in an endless chaotic dance. The universe was not dark, it was blazingly, violently bright, but it was opaque, a thunderstorm made of light trapped inside itself, where every direction you could look would reveal nothing but a blinding wall of brilliance. For nearly 400 millennia, the universe was blind. Light existed, but no eye, real or cosmic, could see. There were no shadows because there was nowhere for light to go, no clear path through the fog. The cosmos was a hall of mirrors with no exit, reflecting its own birth back upon itself in a deafening silence that wouldn't break until atoms learned how to form. In those first moments after inflation, the universe was still unimaginably hot, though cooling rapidly as expansion stretched and thinned the fabric of space-time. At temperatures exceeding 1 trillion degrees, matter existed in a state we can barely reproduce even in our most powerful particle accelerators. A Quark-Gluon Plasma, a seething ocean where quarks, the fundamental building blocks of protons and neutrons, swam freely, unable to bind together because the energy was simply too intense. Gluons, the particles that mediate the strong nuclear force, swarmed between them. And here's the strange part. Gluons themselves carry the charge they're supposed to transmit. It's as if the glue holding particles together is itself sticky, creating chains and networks of binding that become stronger the more you try to pull them apart. Try to separate two quarks, and the strong force doesn't weaken with distance like gravity or electromagnetism. It intensifies, like stretching a rubber band until eventually you pump so much energy into the system that you create new quarks from the vacuum itself. The universe was experimenting with its own rules, testing the boundaries of what forces could do. But as the universe expanded, it cooled, not slowly, not gently, but on cosmic timescales that seem slow, only because we're measuring them against infinity. When temperatures dropped below about 2 trillion degrees, still hot enough to vaporize any conventional matter instantly, quarks began to bind together permanently. 3 quarks clustered into protons and neutrons, the building blocks of atomic nuclei, in a process called hadronization. It was a phase transition, like steam condensing into water, except what was condensing was the fundamental fabric of matter itself. Within the first second after the Big Bang, the Quark-Gluon Plasma crystallized into a universe filled with protons, neutrons, electrons, photons, and neutrinos, all bouncing off each other in a furious thermal bath that would have annihilated anything complex enough to be called structure. And here's where we encounter the first great mystery, the cosmic asymmetry that shouldn't exist, but does. For every billion antimatter particles created in the Big Bang, there were 1,000,000,001 matter particles. Matter and antimatter are mirror images, identical in every way except for the sign of their electric charge, and when they meet, they annihilate each other in a flash of pure energy. Converting mass back into photons according to Einstein's most famous equation, in the first second of the universe's existence, matter and antimatter collided and destroyed each other in cascading waves of mutual annihilation, leaving behind floods of high-energy photons. But because of that tiny imbalance, 1 extra matter particle for every billion pairs, when the slaughter was over, when all the antimatter had been destroyed and taken an equal amount of matter with it, a residue remained. That residue is everything. Every atom in your body, every star in the sky, every galaxy scattered across billions of light-years of space. All of it exists because of a 1 in a billion cosmic asymmetry that physicists still don't fully understand. We exist because the universe played favorites, and we still don't know why. The surviving matter, now purged of its antimatter counterpart, consisted mostly of protons and electrons, along with a smaller number of neutrons and a vast sea of photons, billions of photons for every matter particle, a ratio that persists to this day. These photons were light, yes, but not light as we experience it. They were trapped in a cosmic pinball machine careening through a universe so dense with charged particles that they couldn't travel in straight lines. Every time a photon tried to move, it collided with an electron, scattering in a random direction, only to collide with another electron almost immediately. The mean free path of a photon, the average distance it could travel before hitting something, was incomprehensibly small, far smaller than the distance across an atom today. Light was everywhere but could go nowhere. The universe was opaque, a fog so thick that if you could somehow exist in that moment and open your eyes, you wouldn't see anything but a uniform glowing haze in every direction, like being inside a fluorescent bulb. As tens of thousands of years passed, the universe continued expanding and cooling, but it remained stubbornly opaque. Protons and electrons existed, but they couldn't combine into neutral hydrogen atoms because temperatures were still too high. Any time an electron got close enough to a proton to orbit it, a high-energy photon would slam into it and knock it free again, ionizing the atom before it could fully form. The universe was a plasma, a state of matter where electrons roam free rather than being bound into atoms. And in a plasma, light cannot travel freely because charged particles scatter photons relentlessly. It's the same reason you can't see through the sun. The interior of our star is a plasma so dense that photons generated in the core take hundreds of thousands of years to random walk their way to the surface. Even though light itself could make the journey in less than 3 seconds if it could travel in a straight line. Then, at around 380,000 years after the Big Bang, something extraordinary happened. Temperatures had finally dropped to about 3,000 degrees Kelvin, still hot enough to melt any metal, to vaporize rock, but cool enough for electrons and protons to finally stick together. This moment is called recombination, though the name is misleading because electrons and protons had never been combined before. But the term stuck, and recombination it remains. In a relatively brief window of cosmic time, electrons settled into orbit around protons, forming neutral hydrogen atoms, and suddenly the universe transformed from opaque to transparent. Without free electrons to scatter them, photons could finally travel unimpeded. Light, which had been born in the first instant but imprisoned for hundreds of millennia, was suddenly free. The fog lifted. The universe became clear. This moment, this transition from plasma to neutral atoms, from opacity to transparency, is the moment the cosmic microwave background was born. Every photon that scattered off an electron one last time before recombination began a journey through space-time that continues to this day. These photons have been traveling for 13.8 billion years, cooling as the universe expands, red-shifting from visible light down through infrared and into the microwave portion of the spectrum. Today, they're everywhere. They fill the entire universe with a faint microwave glow at a temperature of just 2.7 degrees above absolute zero. This is the oldest light in existence, the afterglow of creation, a baby photograph of the universe taken when it was less than 1% of its current age. Every time you see static on an old analog television, roughly 1% of that noise is the cosmic microwave background. Photons that have been traveling since before the Earth existed, before the Sun existed, before the Milky Way coalesced from primordial gas clouds. In 1964, two scientists named Arno Penzias and Robert Wilson were trying to eliminate an annoying hum from a radio antenna at Bell Labs in New Jersey. No matter what they did, no matter how carefully they calibrated their equipment, no matter how many times they cleaned pigeon droppings out of the antenna, the hum persisted, a faint microwave signal coming uniformly from all directions in the sky. They didn't realize it at the time, but they were listening to the echo of the Big Bang itself, the hiss of creation reverberating through billions of years. That hum earned them the Nobel Prize and confirmed what cosmologists had predicted. If the universe began in a hot, dense state, it should still be glowing with the cooled remnants of that primordial fireball. But the cosmic microwave background isn't perfectly uniform. If it were, the universe would be boring, a smooth expanse of hydrogen gas expanding forever with no structure, no stars, no galaxies, no life. Instead, when we map the CMB with exquisite precision, as satellites like COBE, MAP, and Planck have done, we find tiny fluctuations. Hot spots and cold spots that differ in temperature by only 1 part in 100,000. These fluctuations are the quantum seeds stretched by inflation, density variations that would eventually grow under gravity into the cosmic web of galaxies we see today. The hot spots correspond to regions that were slightly denser, where gravity would pull matter together more strongly. The cold spots correspond to regions that were slightly less dense, cosmic voids that would remain relatively empty. We're seeing the universe at its most innocent. Before stars had formed, before galaxies had assembled, when the blueprint for all future structure was just barely visible as subtle ripples in the fabric of space-time. And these ripples tell a story that's almost disturbing in its implications. The patterns in the CMB match the predictions of inflation with eerie accuracy. The statistical distribution of hot and cold spots, the angular scale at which fluctuations appear, the slight polarization of the light. All of it fits the model of a universe that underwent exponential expansion in its first moments, stretching quantum uncertainty to cosmological scales. But there are anomalies, features in the data that shouldn't be there according to standard inflation models. There's an unexpected asymmetry between one hemisphere of the sky and the other, a cold spot larger than it has any right to be, hints of patterns that might, just might, be the imprint of something that happened before inflation, perhaps even before the Big Bang itself. Some physicists believe these anomalies could be evidence of collisions with other universes in a multiverse, or echoes of a previous universe that collapsed into ours. Others think they're statistical flukes, artifacts of the fact that we only have one universe to observe, one sample size, and with a sample size of one, strange things can happen by chance alone. But the possibility lingers, tantalizing and troubling in equal measure, that the CMB is not just a baby photo of our universe, but a palimpsest, a document that's been written over, carrying faint traces of something older underneath. There's another pattern hidden in the CMB, something called Baryon acoustic oscillations. Before recombination, when the universe was still a plasma, sound waves, yes, actual acoustic waves, rippled through the primordial soup. These weren't sound waves as we know them, not vibrations traveling through air, but pressure waves moving through the coupled fluid of photons and matter, driven by the gravitational tug of those initial density fluctuations from inflation. When recombination happened and photons decoupled from matter, those sound waves froze in place, imprinted in the distribution of matter as a characteristic scale, a preferred distance at which galaxies would later tend to form. We can still measure this scale today, seeing it in the clustering patterns of galaxies hundreds of millions of light-years apart. It's like the universe rang like a bell in its infancy, and we can still hear the resonance of that ringing encoded in the structure of everything. But underlying all of this is a more fundamental unease. The universe shouldn't exist. The fact that we're here, that matter survived the first second, that protons and electrons found each other to make atoms, that photons escaped the plasma to bring us a record of creation. All of it depends on that 1 in a billion asymmetry between matter and antimatter. If the universe had been perfectly symmetric, if matter and antimatter had been created in exactly equal amounts, they would have annihilated each other completely, leaving behind nothing but a sea of photons expanding into the void. No atoms, no stars, no planets, no life. We are the descendants of an imbalance, the children of an asymmetry that physics can't fully explain. And that should terrify us, because it means the universe could just as easily not have existed. We live in a reality that won by the thinnest of margins, a coin flip where heads meant existence and tails meant eternal emptiness. And somehow, against odds we still don't understand, The coin landed on heads. When light was finally born into freedom at 380,000 years, when the fog lifted and the universe became transparent, it revealed a cosmos balanced on a knife's edge between order and chaos, existence and oblivion. That light has been traveling ever since, carrying with it the story of our impossible origin, whispering secrets about quantum fluctuations and phase transitions and symmetries broken. And embedded in those whispers are hints of something older, something stranger, patterns that suggest the Big Bang might not have been the beginning but merely the latest chapter in a story that has no first page. After the light was born, after recombination freed photons to travel across the cosmos, after the universe became transparent for the first time, something unexpected happened. Nothing. For 100 million years, a span longer than complex life has existed on Earth, the universe went dark. Not dark in the sense of the opaque plasma that came before, but dark in a more profound way. Empty, silent, cold, waiting. The cosmic microwave background faded into infrared as expansion stretched its wavelength, and there were no stars yet to replace it. No galaxies burning with fusion fire. No quasars blazing at the centers of newborn cosmic structures. Just hydrogen. Neutral hydrogen atoms drifting through the void, spreading thinner as space itself expanded, cooling toward the background temperature of the universe, which was itself plummeting toward the deep cold of near absolute zero. The universe had become a graveyard before anything had lived, a monument to potential that had not yet realized itself, a cathedral in perfect darkness waiting for someone to flip the switch. Imagine floating in that emptiness. In every direction, for millions of light years, there would be nothing but hydrogen gas, invisibly thin, perhaps a few atoms per cubic meter, all of it slowly falling together under gravity's patient pull, but still too dispersed, too warm, too structureless to collapse into anything interesting. No landmarks, no reference points, no way to tell if you were moving or stationary because there was nothing to move relative to. Nothing to mark the passage of time except the relentless expansion of space-time itself, which you couldn't see or feel, only infer from the mathematics. This era, appropriately named the Cosmic Dark Ages, was a period of cosmic adolescence, an awkward phase between the violence of birth and the glory of maturity, where the universe simply existed without doing much of anything at all. But beneath the apparent stillness, something was stirring. Those tiny fluctuations imprinted in the cosmic microwave background, those 1 part in 100,000 variations in density, were still there, woven into the fabric of the universe like invisible threads in a tapestry. Regions that were slightly denser than average had a little more gravitational pull. Not much. Not enough to notice over short timescales. But gravity is patient, and it never stops. Slowly, imperceptibly, those denser regions began to attract nearby matter. Hydrogen atoms drifted toward them, nudged by gravitational gradients so gentle they would be impossible to measure directly, but cumulative over millions of years. The dense got denser, the sparse got sparser. Structure was emerging from noise, order crystallizing from chaos, and all of it driven by random quantum jitters that occurred in the first trillionth of a second after the Big Bang, stretched by inflation to cosmic scales, now guiding the assembly of everything that would ever exist. Here's the staggering part. These quantum fluctuations were genuinely random. There was no plan, no blueprint, no cosmic architect deciding where galaxies should form. The seeds of structure, the initial conditions that would determine where your galaxy would be, where the local group would assemble, where great voids and superclusters would emerge, were quantum accidents, Heisenberg uncertainty writ large across the sky. If the universe were rewound and played again, inflation would stretch different quantum fluctuations, and the large-scale structure of the cosmos would look completely different. Earth might not form, the sun might not ignite, humans might never exist. We live in one random realization of infinite quantum possibilities, and the fact that this particular realization happened to be conducive to complexity, to stars, to life, is either the most extraordinary coincidence imaginable or evidence that we're missing something profound about how reality works. But the hydrogen alone couldn't have done it. If the universe contained only the ordinary matter we can see, the protons, neutrons, and electrons that make up atoms, gravity wouldn't have been strong enough to pull gas clouds together quickly enough. The expansion of space-time was working against collapse, stretching matter thinner, making it harder for gravity to overcome the outward momentum. Calculations showed that if only baryonic matter, the technical term for ordinary atomic matter, existed, the first stars wouldn't have formed for billions of years, and the universe we see today, rich with galaxies and structure, would be impossible. Something else had to be there, something invisible, something that didn't interact with light, but did interact with gravity, providing the scaffolding upon which visible matter could collapse. That something is dark matter, and it's one of the most profound mysteries in modern physics. 85% of the matter in the universe is dark. We've never touched it, never seen it directly, never captured a single particle of it in our detectors despite decades of increasingly sophisticated experiments. But we know it's there because we can see its gravitational effects everywhere we look. Galaxies rotate too fast. Their outer edges move so quickly that they should fly apart unless there's far more mass holding them together than we can see in stars and gas. Clusters of galaxies bend light from background objects in ways that require much more mass than the visible matter can account for. The cosmic microwave background's patterns only make sense if dark matter was already clumping together before recombination, providing gravitational wells into which ordinary matter could fall. Dark matter doesn't emit light, doesn't absorb light, doesn't reflect light. It passes through ordinary matter as if we're not even there, interacting only through gravity, the weakest and most universal of forces. During the cosmic dark ages, dark matter was hard at work. While hydrogen drifted aimlessly, dark matter was already collapsing into vast halos, gravitationally bound structures that would become the foundations for galaxies. Because dark matter doesn't interact electromagnetically, it doesn't radiate energy away. When ordinary matter falls into a gravitational well, it heats up, collides with other matter, radiates that energy as light or heat, and settles into stable structures like disks or spheres. Dark matter can't do that. It just falls, and because it can't shed energy through radiation, it remains diffuse, forming enormous halos that extend far beyond the visible edges of galaxies. These halos are the hidden architecture of the universe, the invisible framework that made everything else possible. Without dark matter, galaxies wouldn't exist. Stars wouldn't exist. Planets wouldn't exist. You wouldn't exist. The gravitational potential wells created by dark matter halos were the nurseries where hydrogen could accumulate, where densities could rise high enough for gravity to overcome pressure, where the first stars could finally ignite. We are utterly dependent on something we don't understand, something that constitutes most of the matter in reality, something that could be particles we haven't discovered yet. Exotic relics from the Big Bang, perhaps WIMPs, weakly interacting massive particles, or axions, or sterile neutrinos, or something even stranger. Some physicists think dark matter isn't matter at all, but a sign that our theory of gravity is incomplete, that Einstein's equations need modification on galactic scales. But most evidence points to dark matter being real, physical stuff, and the fact that we've built detectors miles underground, shielded from cosmic rays, cooled to near absolute zero, and still haven't caught a single dark matter particle interacting with our instruments is both humbling and terrifying. As tens of millions of years passed, the dark matter halos grew. They merged with each other when their gravities overlapped, forming larger structures in a hierarchical cascade that would eventually produce the cosmic web, the vast filamentary network of dark matter and gas that fills the universe today, with galaxy clusters at the intersections and enormous voids in between. Hydrogen continued to fall into these dark matter wells, pulled by gravity, accumulating in the deepest potential wells where dark matter was most concentrated. Slowly, the density increased. Slowly, the temperature began to rise as gravitational potential energy converted into thermal energy. Slowly, the conditions for something extraordinary began to assemble. The universe during this time must have been profoundly lonely. If consciousness could exist without stars, without planets, without the complex chemistry that stars forge in their cores and scatter through space when they die, that consciousness would find itself in a cosmos of almost unimaginable monotony. The same hydrogen atoms, repeating endlessly in every direction, with nothing to break the pattern except statistical fluctuations too subtle to perceive. Time would stretch on without events to mark it, without change to give it meaning, existence without experience, potential without realization, a universe holding its breath, waiting for the moment when gravity would finally win its slow war against expansion and ignite the first fusion reactions, the first lights in the darkness, and then, somewhere in a dark matter halo that had accumulated enough hydrogen, somewhere in a cloud that had grown dense enough and hot enough, somewhere around 100 million years after recombination, though the exact timing is still debated, the first star was born. Not gently, not quietly. These first stars, called Population 3 stars, were monsters compared to our Sun, perhaps 100 times more massive, burning thousands of times brighter, living fast and dying young in supernova explosions that would seed the cosmos with the first heavy elements. When that first star ignited, when hydrogen nuclei in its core fused into helium and released floods of energy, when photons streamed outward through the surrounding gas, the cosmic dark ages began to end. That first starlight was ultraviolet, energetic enough to ionize the hydrogen around it, creating a bubble of hot plasma expanding outward from the star. Then another star formed nearby, and another, and clusters of stars, the first galaxies, tiny and irregular compared to the grand spirals and ellipticals that would come later, but galaxies nonetheless, islands of light in the cosmic ocean. The ultraviolet radiation from these early stars began to reionize the universe, splitting neutral hydrogen back into protons and electrons, transforming the cosmos from neutral and transparent to ionized and transparent. A subtle but crucial transition that marks the end of the Dark Ages and the beginning of the era of structure. But here's what haunts cosmologists. We can't see those first stars. They lived and died billions of years ago, and their light has been stretched by cosmic expansion into wavelengths that are extremely difficult to detect. The James Webb Space Telescope, launched in 2021, is designed specifically to peer back into this epoch, to catch the faint infrared glow of those first galaxies forming, to witness the moment when darkness gave way to light. Early results have already surprised us. Galaxies forming earlier and faster than models predicted. Structures appearing more massive and mature than they should be at such early times. Hints that our understanding of galaxy formation might need revision. The Dark Ages were never truly empty. They were full of potential, full of invisible architecture being assembled by dark matter, full of quantum seeds growing toward harvest. The stillness was an illusion. Beneath the apparent monotony, the universe was preparing for an explosion of complexity that would eventually produce stars, planets, chemistry, biology, consciousness, creatures capable of looking back across billions of years and wondering how they came to exist. The darkness was not an ending, but a beginning, not a failure, but a necessary pause, a moment when the universe caught its breath before embarking on the grandest construction project imaginable, building itself into something capable of understanding its own origin. And as the first starlight pierced the void, as ultraviolet photons carved bubbles of ionization through the primordial hydrogen, the universe crossed a threshold from which there could be no return. The Age of Light had begun. The first stars were not like our sun. They were titans, behemoths born from pure hydrogen and helium in a universe that had never seen carbon, never known oxygen, never forged the iron that would one day flow through veins on a distant planet, circling an ordinary yellow star. These population 3 stars, so named because they came before population 2 and population 1 in a backward classification scheme that confuses everyone, were monsters of fusion, some reaching hundreds of solar masses, perhaps even 1,000 times more massive than the star that warms Earth. They burned with an intensity that defies comprehension, their surfaces blazing at temperatures of 100,000 degrees Kelvin, emitting torrents of ultraviolet radiation so fierce it ionized the space around them for hundreds of light years in every direction. Blue, white, and terrible. They were the universe's first experiment with light, and they were doomed from the moment they ignited. Mass is destiny for a star. The more massive you are, the harder gravity crushes your core. The hotter your fusion burns, the faster you consume your fuel, and the shorter your life becomes. Our sun will burn for 10 billion years, a slow and steady furnace that's already halfway through its life cycle. A star 10 times more massive might last only 20 million years. A star 100 times more massive burns through its hydrogen in just a few million years. A cosmic eye blink, a brief flash of brilliance before the inevitable collapse. The first stars lived fast and died young, and in their dying, they gave the universe a gift it had never possessed: complexity. They transformed the simple into the intricate forging elements that would eventually become planets, oceans, DNA, thought itself. Creation, it turns out, requires destruction. The universe had to learn how to kill before it could learn how to build anything interesting. Inside the core of a star, hydrogen nuclei slam together under pressures millions of times greater than anything we can create on Earth, overcoming the electromagnetic repulsion that normally keeps protons apart, fusing into helium and releasing energy in the process. This is the fire that makes stars shine, the reaction that balances gravity's inward crush with radiation's outward push, maintaining a delicate equilibrium that can last for millions or billions of years, depending on the star's mass. But fusion doesn't stop at helium. When a star exhausts the hydrogen in its core, gravity reasserts itself, compressing the core further, raising temperatures until helium begins to fuse into carbon and oxygen. Then, for more massive stars, carbon fuses into neon, neon into magnesium, magnesium into silicon, silicon into iron, each stage requiring higher temperatures, higher pressures, shorter timescales. The star racing through its nuclear options like a gambler desperate for one more hand. This process, stellar nucleosynthesis, is how the periodic table was written. Every element heavier than helium, everything that isn't left over from the Big Bang, was forged in the core of a star, or in the explosive death of one. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, the iron in your blood. All of it was synthesized through fusion reactions inside stars that died before our solar system was even a cloud of gas. You are not metaphorically stardust. You are literally composed of atoms that were once in the cores of distant suns, compressed under unimaginable heat and pressure, then scattered into space when those stars exploded, eventually drifting together into a new generation of stars and planets and life. Every breath you take contains oxygen atoms that were inside a star billions of years ago. Every time your heart beats, it pumps iron that was forged in a supernova shockwave. You are not separate from the cosmos. You are a temporary arrangement of atoms that the universe is using to examine itself. But here's where the story takes a darker turn. Fusion is an energy-releasing process only up to iron. Fuse lighter elements, and you get energy out. Fuse elements into iron, and you break even. Try to fuse iron into heavier elements, and you actually consume energy rather than release it. Iron is the dead end, the ash heap of fusion, the point where the nuclear fire can burn no further. For a massive star, this is catastrophic. When the core converts to iron, fusion stops. No more energy production. No more outward radiation pressure, just gravity, still pulling, still crushing, and nothing left to resist it. What happens next occurs faster than thought itself. The core collapses. In less than a second, a sphere of iron the size of Earth, containing more mass than the Sun, implodes to a ball perhaps 20 kilometers across, compressing matter to densities found nowhere else in the universe except inside neutron stars and black holes. Electrons are crushed into protons, forming neutrons and releasing floods of neutrinos that carry away most of the energy. The collapse accelerates to nearly a quarter the speed of light, then suddenly halts when the core reaches nuclear densities and becomes incompressible. The infalling matter rebounds off this suddenly rigid surface, launching a shock wave outward through the star. This is a supernova, and it's not just an explosion. It's the most violent event in the universe short of the Big Bang itself. A single supernova releases more energy in 10 seconds than the Sun will produce in its entire 10 billion-year lifetime. For a brief moment, one dying star can outshine an entire galaxy containing hundreds of billions of stars. The shock wave tears through the star's outer layers at tens of thousands of kilometers per second, heating them to billions of degrees. And in that inferno, in the fleeting seconds when conditions rival the early universe, the heaviest elements are born. Gold, platinum, uranium, elements heavier than iron that can't be produced by normal fusion, are synthesized in the supernova shock through rapid neutron capture, a process where atomic nuclei are bombarded with neutrons so intensely they don't have time to decay before capturing another neutron and climbing up the periodic table. The gold in your wedding ring, the uranium in nuclear reactors, the rare earth elements in your smartphone, all of it came from supernova explosions forged in the last seconds of a star's life and blasted into space at a significant fraction of the speed of light. The first population 3 stars died this way, seeding the universe with its first metals. Astronomers call everything heavier than helium a metal, much to the confusion of chemists. These elements mixed with the primordial hydrogen and helium, enriching the gas clouds from which the next generation of stars would form. Population 2 stars were born from this slightly enriched gas, and they in turn died and enriched the medium further, eventually producing population 1 stars like our Sun, which contains about 2% metals by mass. That might not sound like much, but it's enough to make planets. You can't build a rocky world from hydrogen and helium. They're gases that won't condense into solid form under normal conditions. You need silicon for rocks, iron for cores, carbon and oxygen and nitrogen for atmospheres and oceans and life. The first stars were made of nothing but primordial hydrogen and helium, because nothing else existed yet. They couldn't have planets. They couldn't have moons. They certainly couldn't have life. They were sterile furnaces whose only purpose was to die so that future generations could be more interesting. But supernovae didn't just create elements. They created something far stranger, something that would come to dominate the structure and evolution of galaxies, something so extreme that the laws of physics themselves break down at their boundaries. When the most massive population 3 stars collapsed, when their cores imploded beyond the point where even neutron degeneracy pressure could hold them up, they didn't stop at neutron star density. They kept collapsing, crushing matter into an infinitely small point, wrapping space-time around themselves so tightly that nothing, not even light, could escape. They became black holes, and the universe suddenly had a new player on the stage, one that would reshape everything it touched. Black holes are not cosmic vacuum cleaners, despite popular imagination. They don't suck in everything around them, any more than any other massive object does through gravity. If the Sun suddenly became a black hole, which it can't, it's not massive enough, Earth would continue orbiting exactly as before, because the mass, and therefore the gravity, would be unchanged. What makes black holes special is their compactness. All their mass is compressed into such a small volume that the escape velocity at a certain radius, the event horizon, exceeds the speed of light. Cross that boundary, and you're gone forever, cut off from the rest of the universe by the absolute cosmic speed limit. Fall toward the center, and space-time curves so severely that all future paths point inward. There's no escape, not because some force is holding you, but because every direction that qualifies as forward in time leads deeper into the black hole. You can no more escape than you can travel backward in time. The first black holes, formed from population 3 stars, were perhaps 10 to 100 times the mass of the Sun. Small by cosmic standards, but significant enough to alter the gravitational landscape of early galaxies. They attracted gas, which spiraled inward, heating through friction as it fell, emitting X-rays and gamma rays before disappearing across the event horizon. They merged with other black holes when their host galaxies collided, growing larger, eventually seeding the supermassive black holes that now lurk at the centers of most galaxies, including our own Milky Way. Sagittarius A star, the black hole at the galactic center, weighs 4 million solar masses and sits just 26,000 light-years from Earth. A silent gravitational anchor around which hundreds of billions of stars orbit. Here's the paradox cosmologists wrestle with. We've found supermassive black holes, billions of solar masses, in galaxies less than 1 billion years after the Big Bang. That shouldn't be possible. Black holes grow by accreting matter and merging with other black holes, processes that take time. Even if you start with the most massive population 3 stars collapsing into 100 solar mass black holes, you can't grow them to 1 billion solar masses in less than 1 billion years using known mechanisms. Something else must have happened. Perhaps direct collapse of massive gas clouds into black holes without going through the star phase first. Or perhaps the early universe was more efficient at feeding black holes than our models predict. Or perhaps we're missing something fundamental about how black holes form and grow in the first epochs after the Big Bang. As the first stars died and enriched the cosmos, as supernovae lit up the darkness, and black holes carved gravitational wells in space-time, the first true galaxies began to assemble. Not the small, irregular clumps of stars that formed initially, but larger structures with hundreds of millions or billions of stars organized by gravity and dark matter into rotating systems that could persist for billions of years. These early galaxies were violent places, far more active and turbulent than the Milky Way is today. Star formation rates were tens or hundreds of times higher. Supernovae exploded frequently enough that the interstellar medium was kept hot and ionized. Galaxy mergers were common because the universe was smaller and denser, and galaxies collided and combined like raindrops on a window. Each cycle of star formation and death added more metals to the mix. After several generations, the gas had been enriched enough that smaller, longer-lived stars could form. Stars like our Sun that would burn steadily for billions of years rather than flashing brilliantly and dying in mere millions. And crucially, with metals in the mix, planets became possible. Rocky worlds could condense from the dust and gas around young stars. Water could exist as solid ice in the outer solar system, or liquid oceans on temperate worlds in the habitable zone. Chemistry became interesting. Carbon could form complex chains, oxygen could oxidize, nitrogen could build amino acids. The stage was being set for the next great transition, from chemistry to biology, from dead atoms to living systems. But let's not get ahead of ourselves. The universe was still young, still violent, still figuring out its own rules through trial and error. Population 3 stars had done their job. They'd seeded the cosmos with the raw materials for complexity. But they're gone now, all of them, burned out billions of years ago. We've never seen one directly. We probably never will. They existed in a brief window of cosmic time that closed within a few 100 million years after the Big Bang, replaced by the second and third generations of stars that inherited the enriched gas they left behind. The first stars are ghosts, their presence inferred from the chemical signatures they left in later generations, from the patterns of element abundances we measure in ancient stars today, from the theoretical models that predict their properties and lifetimes. There's something profoundly melancholic about this. The stars that made our existence possible are gone forever, unknowable except through mathematics and inference. We are the descendants of their ashes, built from the debris of their violent deaths, and we will never meet our ancestors. The universe learned to create by learning to destroy, and that lesson echoes through every level of existence. Stars must die to make planets. Supernovae must explode to forge heavy elements. Old galaxies must collide to trigger new star formation. Even in biology, cells must die to make room for new cells. Organisms must die to return their atoms to the ecosystem. Species must go extinct to open ecological niches for new forms to evolve. Creation and destruction are not opposites. They're partners in an eternal dance, where each step of one enables the next step of the other. The calcium in your bones right now was created roughly 7 billion years ago in a supernova explosion somewhere in the region of space that would eventually become our solar nebula. That calcium atom spent billions of years drifting through the interstellar medium, perhaps passing through multiple molecular clouds, before finally being incorporated into the disk of gas and dust that collapsed to form the sun and planets. It was in rocks first, then dissolved into primordial oceans, then taken up by living organisms, passed through countless generations of bacteria and algae and fish and dinosaurs, released back into the environment through death and decay, cycled through the Earth's crust and mantle and oceans over and over again, across hundreds of millions of years, before finally becoming part of you. You are wearing atoms that are older than the Earth, forged in fires hotter than the surface of the sun, scattered into space by explosions bright enough to outshine galaxies, assembled by gravity into planets, organized by chemistry into molecules, harnessed by biology into life, and arranged temporarily into the pattern you call yourself. The first stars burned bright and died fast, transforming a universe of hydrogen and helium into a universe capable of supporting complexity, chemistry, life, and thought. They were the cosmic phoenixes, rising from the ashes of the Big Bang only to immolate themselves so that something more interesting could emerge from their remains. The universe's first act of creation was an act of self-destruction, and every structure we see today, every galaxy, every star, every planet, every living thing exists because those first stars had the courage to burn brilliantly and die spectacularly. They gave everything they had so that the cosmos could become something more than a thin soup of primordial elements expanding forever into the void. And in doing so, they taught the universe its most important lesson, that endings are also beginnings, that death feeds life, that destruction enables creation, and that sometimes you have to burn down everything to build something worth having. For billions of years after the first stars died, the universe continued its grand construction project, building complexity atom by atom, molecule by molecule, structure by structure, until finally, on at least one unremarkable rocky planet, orbiting an ordinary yellow star in the outer suburbs of an average spiral galaxy, something extraordinary happened. The universe opened its eyes. Not literally. There were no cosmic eyelids, no universal retina, but through the improbable arrangement of carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur into self-replicating molecules that evolved over eons into organisms capable of perception, memory, thought, and wonder. Through you, through us, through every conscious being that has ever looked up at the night sky and asked where it all came from. We are not observers standing outside the universe looking in. We are the universe looking at itself, a way for the cosmos to know itself. As Carl Sagan so beautifully put it, you are not in the universe, you are the universe, localized, concentrated into a pattern complex enough to reflect on its own existence, to trace its lineage back through biological evolution, through stellar nucleosynthesis, through the Big Bang, to the quantum foam from which everything emerged. But getting from dead atoms to living cells, from chemistry to biology, from molecules to minds, required a series of coincidences so improbable that their existence demands explanation. Start with planets. Rocky worlds like Earth can only form in solar systems enriched with heavy elements from previous generations of stars. Silicon for rocks, iron for cores, oxygen for atmospheres, carbon for organic chemistry. The gas and dust that collapsed to form our solar system 4.6 billion years ago contained about 2% metals by mass, the accumulated debris of countless supernovae that exploded and died over the previous 9 billion years. That dust condensed into planetesimals, which collided and merged into protoplanets, which eventually became the 8 worlds we know today, along with countless asteroids, comets, and Kuiper belt objects orbiting in the cold darkness beyond Neptune. Earth formed at precisely the right distance from the Sun, not so close that water would boil away, not so far that it would freeze permanently. The habitable zone, that narrow band where liquid water can exist on a planet's surface, is a cosmic Goldilocks region, and we happen to land right in the middle of it. But distance alone isn't enough. Earth needed a large moon to stabilize its axial tilt, preventing wild climate swings that might have made complex life impossible. It needed plate tectonics to recycle carbon and regulate atmospheric carbon dioxide over geological timescales, maintaining a stable temperature through the carbonate-silicate cycle. It needed a magnetic field, generated by a liquid iron core, to shield the surface from solar wind and cosmic radiation that would otherwise strip away the atmosphere and sterilize the surface. It needed Jupiter, massive enough to gravitationally perturb comets and asteroids, either flinging them out of the solar system or occasionally directing them toward Earth to deliver water and organic compounds. but not so close that its gravity would disrupt Earth's orbit entirely. Every one of these conditions had to be met. Remove the Moon, and Earth's axis would wobble chaotically. Remove plate tectonics, and the planet would likely end up like Venus, a runaway greenhouse where oceans boiled away and carbon dioxide accumulated until surface temperatures exceeded 400 degrees Celsius. Remove the magnetic field, and solar wind would strip the atmosphere over millions of years, leaving a dead, airless rock like Mars. Each requirement was necessary but not sufficient. You needed all of them together, along with countless other factors we're still discovering, to create a world where life could not only emerge but persist for billions of years, surviving multiple mass extinctions, adapting and complexifying until something capable of asking, "Why are we here?" finally evolved. And then there's chemistry. Life as we know it is built from carbon, and there are good reasons for this. Carbon forms 4 strong covalent bonds, allowing it to create complex chains, rings, and branching structures that no other element can match. Silicon can form 4 bonds too, but silicon-silicon bonds are weaker and break easily in the presence of oxygen and water, making silicon-based biochemistry implausible on worlds with oxidizing atmospheres. Carbon, combined with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, can build the full repertoire of biological molecules. Proteins, nucleic acids, lipids, carbohydrates, the entire molecular machinery of life. But this requires liquid water as a solvent, temperatures mild enough that complex molecules don't decompose, but warm enough that chemical reactions proceed at reasonable rates, and an energy source, sunlight, chemical gradients, geothermal heat, to drive the system away from thermodynamic equilibrium, because life is fundamentally a dissipative structure that maintains order by exporting entropy to its environment. Somewhere in Earth's primordial oceans, perhaps in hydrothermal vents where hot, mineral-rich water met cold seawater, or in shallow pools where lightning and UV radiation provided energy, simple organic molecules began linking together into more complex structures. Amino acids formed peptides. Nucleotides polymerized into RNA. Lipids spontaneously assembled into vesicles, primitive cell membranes that could encapsulate chemical reactions and separate inside from outside, self from non-self. At some point, we still don't know exactly when or how these chemicals crossed a threshold. They began replicating. They began evolving. They became alive. The transition from chemistry to biology is one of the deepest unsolved problems in science. The moment when dead molecules arranged themselves into patterns capable of reproduction, metabolism, and evolution. When matter became capable of wanting to continue existing. Once life began, evolution took over, operating through the simple but powerful logic of variation and selection. Random mutations introduced changes. Environmental pressures selected which variants survived and reproduced. Over billions of years, single-celled organisms evolved into multicellular ones. Simple nerve nets evolved into complex brains. Organisms that could sense and respond to their environment had advantages over those that couldn't. Eventually, some organisms developed sophisticated enough nervous systems that they became conscious, capable not just of responding to stimuli, but of experiencing, of having an inner life, of suffering and joy and curiosity and fear. And at least one species developed language, abstract thought, cumulative culture, technology, and the ability to look back across billions of years and reconstruct the story of its own cosmic origins. Here's where the story becomes almost unbearably strange. The universe seems fine-tuned for our existence, calibrated with exquisite precision to allow stars, planets, chemistry, and life. If gravity were just 1% stronger, stars would burn through their fuel too quickly, collapsing before life had time to evolve on orbiting planets. If gravity were 1% weaker, stars might never ignite fusion at all, remaining as cold clouds of hydrogen that never forged heavy elements. If the electromagnetic force were slightly different, atoms wouldn't be stable, electrons might not bind to nuclei, or chemical bonds might not form, making molecules impossible. If the strong nuclear force were 5% weaker, deuterium wouldn't form, and stars couldn't burn hydrogen into helium, shutting down stellar nucleosynthesis entirely. If it were 5% stronger, protons would bind together so readily that hydrogen would have fused into heavier elements in the first minutes after the Big Bang, leaving no hydrogen for stars or water. The list goes on. The ratio of electromagnetic force to gravitational force is about 10 to the 36. Change it even slightly, and you get a universe where either gravity dominates, everything collapses into black holes, or electromagnetism dominates, nothing clumps together at all. The cosmological constant, the energy density of empty space that drives cosmic acceleration, is about 10 to the negative 120 in natural units. Increase it substantially, and the universe expands so fast that galaxies never form. The mass difference between neutrons and protons is just 0.1%, but if it were much larger or smaller, either protons would decay too quickly or neutrons would be too stable. And in either case, the chemistry we need wouldn't work. Every fundamental constant, every physical law, every ratio and relationship seems calibrated to sit within a narrow window that permits complexity. This is the anthropic principle, and it comes in two flavors. The weak anthropic principle simply observes that we can only exist in a universe compatible with our existence. It's a tautology, true but not particularly illuminating. The strong anthropic principle suggests something more troubling. The universe must have properties that allow observers to eventually arise within it. This seems to imply purpose, design, cosmic intentionality, which makes scientists deeply uncomfortable because it flirts with teleology, the idea that things happen for a purpose rather than through mechanistic cause and effect. Yet the fine-tuning is undeniable, the odds of all these constants falling within. Life-permitting ranges by chance alone are so astronomically small that some physicists believe we must be missing something fundamental. One explanation is the multiverse, the idea that our universe is just one bubble in an infinite foam of universes, each with different physical laws, different constants, different properties. In this framework, most universes are sterile, unable to support complexity, let alone life. But if there are enough universes, infinite universes, then somewhere, by sheer statistical inevitability, there will be universes where the constants happen to fall within life-permitting ranges. We exist in one of those rare universes, not because it was designed for us, but because we couldn't possibly exist in the overwhelming majority of universes where the constants are wrong. It's selection bias on a cosmic scale. We find ourselves in a life-permitting universe for the same reason fish find themselves in water. We wouldn't be here to wonder about it otherwise. But this explanation comes with philosophical baggage. If the multiverse exists, most of it is forever unobservable, cut off from us by the boundaries of space-time, making it unfalsifiable in the traditional scientific sense. We can't test it, can't gather evidence for or against other universes, can only appeal to theoretical elegance and mathematical consistency. Some physicists embrace the multiverse because it solves the fine-tuning problem without invoking design. Others reject it as metaphysics masquerading as physics. The debate rages on, unresolved, perhaps unresolvable. A question that sits at the uncomfortable boundary between science and philosophy. Another possibility, darker and lonelier. We might be alone. The emergence of life might be so improbable. The chain of contingencies leading from chemistry to consciousness so fraught with failure points that intelligent life is vanishingly rare. Fermi's paradox haunts us. If the universe is billions of years old and contains hundreds of billions of galaxies, with hundreds of billions of stars each, where is everybody? We've been listening for signals from extraterrestrial civilizations for decades and heard only silence. We've found thousands of exoplanets, but no signs of life, no techno-signatures, no evidence that we're part of a larger cosmic community. Maybe life is common, but intelligence is rare. Maybe intelligence is common, but technological civilizations destroy themselves before they can spread across the stars. Maybe the Great Filter, some catastrophically difficult step in the evolution from chemistry to spacefaring civilization, lies behind us. And we're the lucky ones who made it through. Or maybe it lies ahead, and we're doomed to join all the other extinct civilizations whose radio signals faded before reaching anyone's ears. Or maybe we're simply early. The universe is only 13.8 billion years old, but it will continue for trillions of years, possibly forever, if dark energy continues accelerating expansion. Stars will keep forming for perhaps another 100 trillion years before the last clouds of hydrogen finally disperse and star formation ceases. If life takes billions of years to evolve complex intelligence, and if there's nothing special about this particular epoch, then we might be among the first intelligent species to emerge. The cosmos might eventually teem with life, but we arrived during the quiet opening act, before the main show began. We're the early birds, wondering why the stage is so empty, not realizing that most of the cast hasn't been born yet. But here's what haunts cosmologists who peer far into the future. The universe's expansion is accelerating, driven by dark energy, and this acceleration will eventually become so extreme that distant galaxies recede from us faster than light can travel. Already, galaxies beyond about 16 billion light-years are receding superluminally. Their light will never reach us because the space between us is stretching faster than photons can traverse it. As expansion continues, this cosmic horizon will shrink. Galaxies we can see today will cross the horizon and disappear. In about 150 billion years, every galaxy outside our local group will have receded beyond the horizon, their light redshifted into invisibility. Any civilization arising after that point will look out and see only their own galaxy and its satellites, isolated in an otherwise empty universe. They won't see the cosmic microwave background. It will have redshifted into undetectability. They won't detect the Hubble expansion. All the distant galaxies they might have measured will be gone. They'll have no evidence the Big Bang ever happened, no way to reconstruct cosmic history, no reason to suspect the universe had a beginning, or that space is filled with billions of galaxies beyond their horizon. We live in a privileged epoch, a narrow window where the universe is old enough for intelligent life to evolve, but young enough that we can still see the cosmic microwave background, still measure the expansion rate, still detect distant galaxies, and reconstruct 13.8 billion years of history. Future civilizations won't have that luxury. They'll think they live in a static, eternal cosmos, a single island of stars surrounded by infinite darkness. They'll be wrong, but they'll have no way to know it. The universe is hiding its past from its own future inhabitants, and we're among the lucky few who can still see the truth before it fades beyond the horizon. You are the universe becoming conscious of itself. A pattern of atoms organized by 4 billion years of evolution into something capable of asking where it came from and where it's going. You're made of stardust and quantum fields and mathematical laws that somehow gave rise to sensation, emotion, curiosity, love. You're impossibly improbable and simultaneously inevitable. A miracle if there's only one universe, a statistical certainty if there are infinite universes, and either way, here you are. Reading these words, aware of your own existence, heir to 13.8 billion years of cosmic history that began in quantum foam and ended up, for now, with you, but the universe isn't done creating. It's about to do something unimaginable, something that will dwarf even the emergence of life and consciousness, something that will fundamentally reshape reality itself in ways we're only beginning to glimpse. The story isn't over, it's barely begun. The Big Bang wasn't special. That might be the most shocking revelation of 21st century cosmology. Not that the universe had a beginning, but that it might have many beginnings, perhaps infinite beginnings, scattered across a landscape so vast that our observable universe, with its 100 billion galaxies and 13.8 billion year history, is merely one bubble in an infinite foam of creation events, each with its own physical laws, its own constants, its own story. The birth we've been describing, the explosion of space-time from quantum nothingness, the inflation that stretched quantum fluctuations to cosmic scales, the cooling that allowed particles and atoms and stars to form. All of it might be happening elsewhere, elsewhen, in ways we can barely conceive. What if the universe has been born and died infinite times? What if birth itself is not an event but a process, eternal and ongoing, with no true beginning and no final ending? Just an endless cycle of creation and destruction playing out across dimensions we cannot see, and timescales that dwarf even the age of our cosmos? Start with eternal inflation, perhaps the most mind-bending extension of the inflationary paradigm that already rewrote our understanding of the early universe. Remember that inflation was driven by a field, the inflaton, sitting in a high-energy state, a false vacuum pregnant with potential energy. When that field decayed to a lower energy state, inflation ended, and the energy released became the hot Big Bang, the particles and radiation that would evolve into everything we see. But here's the catch. Quantum mechanics is probabilistic, and the inflaton field doesn't decay everywhere simultaneously. In some regions of space, the field decays and inflation stops, creating a bubble universe like ours. But in other regions, inflation continues, and those regions expand so fast that they more than compensate for the volume lost to bubble formation. The inflating space grows exponentially, faster than bubbles can eat into it, meaning inflation never truly ends. It's eternal, constantly spawning new bubble universes, while the space between them continues inflating forever. Each bubble is causally disconnected from the others. Light from another bubble universe can never reach us because the inflating space between us is expanding faster than light can travel. We're trapped inside our bubble, able to see only about 46 billion light-years in any direction. The distance light has been able to travel since our Big Bang, accounting for cosmic expansion. But the universe beyond that horizon might extend infinitely, filled with other bubbles, other Big Bangs, other universes with their own observers wondering if they're alone. And because quantum fluctuations are random, because the decay of the Inflaton field happens probabilistically, each bubble can have different properties, different cosmological constants, different strengths for fundamental forces, different numbers of spatial dimensions, different particles and symmetries. Most bubbles will be sterile, unable to support complexity. But given infinite bubbles, and eternal inflation produces infinite bubbles, every possibility that quantum mechanics allows will be realized somewhere. This is the string theory landscape, a theoretical framework suggesting there might be 10 to the 500th power distinct vacuum states, each corresponding to a different possible universe with different physical laws. 10 to the 500th is a number so large it's almost meaningless, far more than the number of atoms in our observable universe, more than the number of Planck volumes in the entire cosmos, more than the number of possible quantum states of everything we can see. Each of these vacua represents a potential universe, and if eternal inflation is correct, all of them exist somewhere in the vast multiverse. Our universe, with its life-permitting constants and forces, is just one lottery ticket among 10 to the 500th, and we find ourselves holding it, not because it was designed for us, but because we couldn't possibly exist in the overwhelming majority of universes where the constants are wrong. Then there's quantum many worlds, a different kind of multiverse entirely. Every time a quantum measurement occurs, every time a particle's wave function collapses, every time a quantum superposition resolves into a definite outcome, the universe splits into multiple branches, one for each possible outcome. In one branch, the electron spins up. In another, it spins down. Both branches are equally real, existing in parallel, forever separated from each other by quantum decoherence. This interpretation of quantum mechanics, first proposed by Hugh Everett in 1957 and largely ignored for decades, has gained traction among physicists because it solves the measurement problem without requiring wave function collapse, without invoking observers or consciousness, without adding mysterious non-local mechanisms to the equations. The math of quantum mechanics is perfectly deterministic and reversible. It's only when we try to interpret what happens during measurement that things get weird. Many World says nothing special happens during measurement. The wave function never collapses, it just branches, and we find ourselves in one branch, unaware of all the others. If many worlds is correct, then every quantum event since the Big Bang has spawned countless branches, and the number of parallel universes containing versions of you is staggeringly large, though not infinite, because there are limits to how many distinguishable quantum states can exist in a region of space-time. Somewhere in the multiverse, there's a version of you who made different choices, took different paths, lived a different life. Somewhere, there's a version of Earth where dinosaurs never went extinct, where humans never evolved, where the sun failed to form and the solar nebula dispersed into the void. And somewhere, perhaps, there's a branch where the outcome of quantum fluctuations in the early universe led to slightly different initial conditions, yielding a cosmos that looks nothing like ours. But maybe the universe doesn't need a multiverse to be eternal. Maybe it's been recycling itself, dying and being reborn in an endless cosmic cycle that has no beginning and no end. This is the idea behind cyclic cosmology, and it comes in several flavors, each attempting to explain how the universe might avoid a true beginning or ending. The Big Bounce hypothesis suggests that the Big Bang wasn't the beginning. It was a transition, the moment when a previous contracting universe reached maximum density and rebounded, like a ball bouncing off the ground, launching into a new phase of expansion. In this model, the universe oscillates eternally, expanding, slowing, eventually recollapsing under its own gravity, compressing into a hot, dense state similar to the early Big Bang, then bouncing back and expanding again in an infinite cycle. Each cycle might last trillions of years, and we're living in just one iteration of an infinite series, unable to see evidence of previous cycles because the bounce erased most information about what came before. Roger Penrose has proposed an even stranger idea: conformal cyclic cosmology. According to Penrose, the far future of our universe, when all stars have died, all black holes have evaporated through Hawking radiation, and nothing remains but a thin soup of photons and other massless particles expanding into the void, is mathematically equivalent to the Big Bang of a new universe. Time and scale lose meaning in a universe with no massive particles, no clocks, no rulers. The infinite future of one universe becomes the Big Bang of the next, in a conformally transformed space-time where the end and beginning are connected. Each cycle, or aeon, lasts perhaps a googol years, 10 to the 100 years, but subjectively feels instantaneous from the perspective of the massless particles that remain. Penrose even claims to see evidence for this in the cosmic microwave background. Circular patterns that might be the imprints of colliding black holes from the previous aeon, gravitational wave signatures that survived the transition and left their mark on our cosmic baby photo. Most physicists remain skeptical. The evidence is weak, the models speculative, the mechanisms unclear. But the ideas are seductive because they answer the question that has haunted us since the beginning: what came before? If the universe is cyclic, there is no before, just an infinite regression of aeons stretching into the past and future, each giving birth to the next, none holding any special status as the beginning. The Big Bang becomes lowercase, one of infinite Big Bangs, and the question of ultimate origins dissolves into the realization that origins might be an illusion, a cognitive bias imposed by minds evolved in a universe with clear causal chains and temporal arrows. But let's confront the alternative. The universe might truly end. Not loop back, not bounce, not transition into a new aeon, but simply run down like a clock whose spring has wound to its limit. The far future, extrapolated from our current understanding of cosmology, is not comforting. If dark energy continues accelerating expansion, and all evidence suggests it will, the universe faces heat death. the gradual dissipation of all available energy into maximum entropy, a state where no work can be done, no complexity can be maintained, no life can exist. Stars will exhaust their fuel. The last red dwarfs will flicker out in about 10 trillion years. Galaxies will evaporate as stars are gravitationally ejected into intergalactic space or fall into central black holes. Those black holes will slowly evaporate through Hawking radiation, taking perhaps 10 to the 100 years to completely disappear, leaving behind nothing but photons scattered across an ever-expanding void. In this distant future, the universe will approach absolute zero. The cosmic microwave background, already cooled to 2.7 degrees Kelvin, will redshift into invisibility. Photons will be stretched to wavelengths larger than the observable universe. Entropy will reach its maximum. Time will lose meaning, because there will be no events, no changes, no processes to mark its passage. Just cold, empty space expanding forever, with isolated particles separated by distances so vast that they will never interact again. This is the heat death, the final equilibrium, the universe's last exhalation before eternal silence. Unless it's not. Some models predict a big rip, where dark energy's density increases over time rather than remaining constant, eventually becoming so strong that it tears apart galaxies, then solar systems, then planets, then atoms, then even space-time itself, shredding the fabric of reality in a cosmic catastrophe that ends not in cold silence, but in violent fragmentation. Other models allow for a big crunch if dark energy is temporary, or if the universe's mass density is higher than we think, causing expansion to eventually reverse, pulling everything back together into a singularity that might or might not bounce back into a new universe. We don't know which fate awaits us because we don't fully understand dark energy, don't know if it's truly constant or evolving, don't know if our universe is open, closed, or flat at scales beyond our ability to measure. Yet even in heat death, even in the cold darkness at the end of time, there's a glimmer of hope, or perhaps horror, depending on your perspective. Quantum mechanics never sleeps. Even in empty space, quantum fields fluctuate. Virtual particles pop in and out of existence. And given enough time, truly staggering amounts of time, far beyond anything we can meaningfully imagine, a quantum fluctuation large enough to spawn a new universe could occur. This is Boltzmann's nightmare made cosmic. Wait long enough, and random fluctuations will eventually produce anything, including another Big Bang, another inflationary epoch, another bubble of space-time expanding into a new universe with new laws and new possibilities. The probability is infinitesimally small, but infinity is a long time, and quantum mechanics deals in probabilities, not certainties. So perhaps the birth of the universe never truly ends, because birth itself is woven into the fabric of quantum reality, an inevitable consequence of the fact that empty space is never truly empty, that fields never stop fluctuating, that given infinite time, even the most improbable events become certainties. The Big Bang might not be a unique historical event, but a recurring phenomenon, happening over and over across eternity, each time creating a new cosmos that expands, evolves, complexifies, produces stars and galaxies, and perhaps life and consciousness, then eventually fades or collapses or tears apart, only to be followed, after unimaginable stretches of emptiness, by another fluctuation, another beginning, another story. This could be your trillionth universe. You might have existed before in different forms, in different configurations of atoms obeying different laws, with no memory of those previous existences, because information doesn't survive across cosmic rebirths. Or perhaps it doesn't matter whether this is the first universe or the billionth. Each one is isolated, complete unto itself, its inhabitants unaware of what came before or what will come after. The multiverse, whether spatial or temporal, whether produced by eternal inflation or quantum many-worlds or cyclic bounces, is a humbling concept because it demotes our universe from the entirety of existence to merely one example among countless others, unremarkable except to those of us fortunate or cursed enough to find ourselves here. But here's the existential comfort hidden in all this cosmic speculation. If the universe's birth is not unique, if it's part of an eternal process that never truly begins or ends, then creation itself becomes a fundamental property of reality rather than a singular miraculous event requiring explanation. The question, why is there something rather than nothing, loses its sting, because there has always been something, will always be something, in one form or another, across one cosmos or another. Existence is not contingent. It's necessary, eternal, unavoidable. The universe doesn't need a first cause because causation might loop back on itself or extend infinitely into the past. Birth is not an event. It's a process, ongoing and eternal, happening everywhere and everywhen across the vast landscape of possible universes. We live in the one era of cosmic history where we can still see the afterglow of our particular Big Bang, still measure the expansion rate, still reconstruct the 13.8 billion-year journey from quantum foam to consciousness. Future civilizations will envy us for this privilege, for being present during the brief window when the universe's origin story is still visible in the sky. But we should also envy ourselves, right now, for being here to witness it, to understand it, to trace our lineage back through stellar nucleosynthesis and quantum fluctuations to the first moment when space-time decided to exist. The birth of the universe was not a one-time event finished long ago. It's a process that never truly ends, echoing across eternity in infinite variations, and we are its witnesses, its products, its way of knowing itself. The universe was born. The universe is being born. The universe will always be born, forever and ever, without end. You are 13.8 billion years old. Not your body, not your memories, not the pattern of thoughts that you call yourself, but the atoms you're made from, the particles that comprise your cells, the energy that animates your existence. Every carbon nucleus in your DNA was forged in the belly of a dying star. Every oxygen molecule you breathe was created when that star exploded in a supernova bright enough to outshine galaxies. The hydrogen in your water, the most abundant element in your body, is even older. It dates back to the first 3 minutes after the Big Bang, when the universe was a seething plasma of protons and electrons hot enough to fuse hydrogen into helium, but cool enough that some hydrogen escaped that primordial fire and survived, drifting through space for billions of years, eventually finding its way into molecular clouds, then planets, then oceans, then you. You are not separate from this story. You are the story, a temporary eddy in the river of atoms flowing from the Big Bang through stars, through space, through Earth, through the long chain of biological evolution that produced organisms complex enough to look back and ask where they came from. The search for the universe's origin has always been the search for our own origin, though we didn't always know it. Ancient creation myths tried to explain how something came from nothing, why there's a world at all, what our place in it might be. They gave us gods and cosmic eggs and eternal cycles because the alternatives, that existence is random, that we're accidental, that the universe doesn't care whether we're here, were too terrifying to contemplate. But science has given us something those myths couldn't, an actual answer, traced backward through evidence and mathematics and observation, from the present moment to the instant of creation itself. And the answer is stranger, more beautiful, more unsettling than any myth could be. The universe began as a quantum fluctuation, smaller than an atom, that inflated exponentially, cooled, condensed into particles, assembled into atoms, collapsed into stars, exploded into heavier elements, formed into planets, organized into life, evolved into consciousness, and now looks back at its own beginning through your eyes. You are hydrogen that learned to wonder where it came from. You are the universe examining itself, asking questions about its own nature, tracing its lineage back through time and space to the moment when there was no time, no space, only potential waiting to become actual. Every time you think a thought, neurons in your brain fire, ions flow across membranes, chemical reactions cascade through synapses, and all of it, the sodium, the potassium, the calcium, the proteins, the water, all of it was cooked in stellar cores or synthesized in supernova shock waves or preserved from the primordial plasma of the early universe. You carry the Big Bang inside you. You are made of it. The distinction between you and the cosmos is grammatically convenient, but physically meaningless. There is no boundary where you end and the universe begins. You're a pattern in the cosmic fabric, a temporary configuration of matter and energy that the universe has arranged into something capable of self-reflection. And here's the profound irony. The universe gave birth to you so it could ask how it was born. For 13.8 billion years, matter and energy swirled through space, obeying physical laws, building structure, but there was no meaning, no purpose, no witness to the grand unfolding. Stars ignited and died without anyone to see them. Galaxies collided without anyone to measure them. The cosmic microwave background radiated through the void without anyone to decode the information it carried. Then, on at least one rocky planet, chemistry became biology. Biology became neurology. Neurology became consciousness. And suddenly, the universe had a mirror. It could see itself. It could ask questions. It could wonder why there's something rather than nothing, how space-time came to exist, what laws govern the dance of particles and forces that make up reality. You are that mirror. When you look up at the night sky and feel awe, when you contemplate the Big Bang and feel vertigo at the thought of existence emerging from nothingness, you're not separate from what you're contemplating. You're the universe feeling awe at itself. This changes everything. If you understand that you're not a separate observer but an integral part of the cosmic process, then your life becomes more than a brief flicker between birth and death. You become a chapter in the longest story ever told. A story that began with quantum foam and might continue forever through eternal inflation, or cyclic bounces, or heat death followed by quantum resurrection. The atoms in your body have been recycled countless times. They were in stars, in nebulae, in ancient oceans, in organisms long extinct, in rocks weathered by wind, in air breathed by creatures who lived and died before humans even existed. When you die, those atoms will return to the ecosystem, be taken up by other organisms, eventually perhaps escape into space, drift through the galaxy, be pulled into a new star, and the cycle continues. You are temporary, but you're made of something eternal, matter and energy that can neither be created nor destroyed, only transformed. We live in a privileged moment, perhaps the only moment in cosmic history where intelligent beings can witness their own birth. The cosmic microwave background is still visible, still carrying information about the first 380,000 years after the Big Bang. We can measure the expansion rate, calculate backward to the initial singularity, reconstruct the conditions in the early universe with astonishing precision. But this window won't stay open forever. As the universe continues expanding, as dark energy accelerates that expansion, distant galaxies will recede beyond the horizon where their light can reach us. The cosmic microwave background will redshift into invisibility. Future civilizations arising trillions of years from now will look out at a dark, empty cosmos with no evidence that the Big Bang ever happened. No way to reconstruct cosmic history. No reason to think they're part of something larger. They'll think they live in an eternal static universe, and they'll be wrong, but they'll have no way to know it. We're here during the brief era when the universe's origin story is still legible in the sky, and that's a gift we should not take for granted. So, don't waste it. Look up. See the stars. Not just pinpoints of light, but nuclear furnaces burning hundreds of light years away. Their light traveling through space for decades or centuries or millennia before reaching your retina. When you see a star, you're seeing the past. You're looking back in time. The farther you look, the further back you see, until at the edge of the observable universe, you're looking at light that's been traveling for over 13 billion years. Light emitted by the first galaxies forming in the cosmic dawn. Light that began its journey when the universe was young and will end its journey in your eye, completing a billion-year arc from there to here, from then to now. Every photon that hits your retina is a messenger from the past, carrying information about when and where it was emitted. And the oldest photons, the ones in the cosmic microwave background, are messengers from the moment of creation itself, stretched and cooled by expansion but still present, still detectable, still whispering the secrets of our origin to anyone who knows how to listen. The Big Bang is both the most distant event in time and the closest. It happened 13.8 billion years ago, but it's also happening now, in every atom, in every force, in every interaction. The expansion that began then continues today. The cooling that started in the first second continues today. The structures seeded by quantum fluctuations in the first trillionth of a second are still growing today. The universe is not something that was born once in the distant past. It's something that's always being born, moment by moment, in an ongoing process of creation that includes you, includes your thoughts, includes this very instant as you read these words and contemplate your place in the cosmos. You are not witnessing the aftermath of creation. You are part of creation. You are creation, experiencing itself from the inside. Every time you look at the stars, You're looking back in time, toward the moment when there were no stars, no atoms, no space, only potential waiting to become actual. And in that looking, in that questioning, in that wonder, you're fulfilling the universe's deepest purpose, to know itself, to understand itself, to become conscious of its own existence and origin. The universe was born so that someday, somewhere, something made of its own matter and energy could ask how it was born. And now you know. You know the story of quantum fluctuations and inflation, and stellar nucleosynthesis and cosmic evolution that led from nothing to everything, from simplicity to complexity, from matter to mind. You know that you're made of stars, that you're 13.8 billion years old, that you're the universe looking at itself in the mirror and seeing, for the first time, how beautiful it is. The universe is always being born, and so are you.